Right now, while you're reading these words, a machine that should have died decades ago is transmitting a signal that scientists are calling impossible. Not unusual, not surprising, impossible. It is not a new telescope, it is not a satellite orbiting Earth, it is not one of the flashy new missions you hear about in the news. It was built before smartphones existed, before the internet existed, before most of the people currently analyzing its data were even born. It runs on a sliver of the power your kitchen microwave uses in a single minute, and what it just confirmed, buried in a data stream that took over 16 hours to travel across empty space to reach us, is not a small correction to an existing theory. It is a finding that is forcing physicists to admit that something they believed with near total confidence about the edge of our solar system is simply wrong. This is the story of Voyager 2. And here is the part almost nobody is talking about. This is not old news. This is not a recap of a discovery that happened years ago and quietly faded from the headlines. This is happening right now in 2026, as NASA runs an experimental procedure on this exact spacecraft, a procedure so risky the engineering team internally nicknamed it the Big Bang, that could either extend its life by years or end it permanently within days, with no way to reverse the decision once it is made. Stay with me, because by the end of this you will understand why researchers are using the word impossible without exaggeration, why what this machine found does not just describe the empty dark between the stars, and why it actually describes the shield that keeps every living thing on this planet alive. I am Mark and this is your channel. Subscribe now if you want more stories like this, because we are just getting started. Let's go back to the beginning, because the story of Voyager 2 is stranger than most people remember, and it starts with a naming decision that confuses almost everyone who hears it for the first time. On August 20th, 1977, a rocket lifted off from Cape Canaveral carrying a spacecraft that launched 16 days before its twin, and yet was still given the number 2. That is not a clerical mistake. It reflects the order the two missions were expected to reach their destinations, not the order they left Earth. Voyager 1 was placed on a faster, more direct trajectory designed to slingshot past Jupiter and Saturn, and then angle sharply upward out of the plane of the solar system entirely, sacrificing any chance of reaching the outer ice giants in exchange for a closer pass by Saturn's massive moon Titan and a quicker path toward interstellar space. Voyager 2 was given something far rarer, a long patient 4-planet route that would use the gravitational pull of each giant world it passed to fling itself onward to the next one, in a specific planetary alignment that occurs roughly once every 175 years. Miss that window and no other spacecraft could realistically attempt the same journey again for generations. Voyager 2 passed Jupiter in July of 1979, capturing detailed images of the planet's turbulent atmosphere and confirming active volcanic eruptions on the moon Io that Voyager 1 had first detected months earlier. It reached Saturn in August of 1981, gathering data on the planet's rings that revealed a level of structure and complexity that Earth-based telescopes had never been able to resolve. Then it kept going, deeper than any spacecraft had ever traveled, toward a planet no human-made object had ever approached at all. In January of 1986, Voyager 2 became the only spacecraft in history to fly past Uranus, discovering 10 previously unknown moons and 2 new rings, and measuring a magnetic field so wildly offset from the planet's rotation axis that engineers at the time genuinely questioned whether their own instruments were malfunctioning. They were not. Uranus simply has one of the strangest magnetic fields in the entire solar system, and we only know that because one aging spacecraft happened to fly close enough to measure it. 3 years later, in August of 1989, Voyager 2 reached Neptune, the final planetary encounter of the entire Voyager program. It discovered 6 new moons, measured supersonic winds racing across Neptune's atmosphere at nearly 1,500 miles per hour, the fastest winds ever recorded anywhere in the solar system, and photographed active nitrogen geysers erupting from the icy surface of Neptune's largest moon, Triton, a world so strange that scientists still believe it was not born there at all, but captured from the distant Kuiper belt by Neptune's gravity billions of years ago. To this day, nearly 50 years later, no other spacecraft in human history has visited all 4 outer planets. Voyager 2 remains the only one. It is quite literally the single most traveled scientific instrument our species has ever built. But the part of the mission nobody planned for, the part that turned this into something far bigger than a planetary tour, came decades later. On November 5, 2018, Voyager 2 crossed the Heliopause, the outer edge of the bubble carved out of interstellar space by the Sun's constant outward stream of charged particles, and became only the second human-made object in history to leave the solar system entirely. Voyager 1 had already made that crossing 6 years earlier, in August of 2012, and for those 6 years the entire scientific understanding of what actually happens at the edge of our solar system rested on Voyager 1's data alone. Here is the detail that almost never makes it into the popular version of this story, and it is the single most important fact for understanding why Voyager 2 turned out to matter so much. Voyager 1's plasma science instrument, the specific device engineered to directly measure the temperature, density, and flow velocity of charged particles both inside the heliosphere and beyond it, had stopped functioning in 1980. It failed before the spacecraft had even reached Jupiter on its outbound journey, more than 3 decades before it ever crossed the Heliopause, which means that when Voyager 1 made the single most scientifically significant crossing of its entire 50-year mission, it did so effectively blind to the one measurement scientists needed most. They had to infer what the plasma was doing from other instruments, from the magnetometer, from the cosmic ray detector, from the plasma wave subsystem, working around a hole in the data that had existed since before most of the current mission team was born. Voyager 2's plasma instrument never failed. It was still fully operational when the spacecraft crossed the Heliopause in 2018, and what it measured at that exact boundary produced a dataset that researchers would later describe, in 5 papers published simultaneously in the journal Nature Astronomy, as historic. For the first time in human history, scientists had a direct, uninterrupted measurement of the plasma on both sides of the true edge of our solar system, taken by an instrument actually sitting inside that boundary as it happened. And what that instrument recorded did not simply confirm what everyone expected, it contradicted it piece by piece in ways the field is still working through. Here is where the first twist in the story arrives. For decades, models built by respected physicists using the best available theory predicted that the heliopause would behave essentially like a wall, a narrow, sharp line, perhaps a few 100,000 miles wide at most, where the hot solar wind blowing outward from the sun would simply run out of pressure and stop, and the colder, denser plasma of true interstellar space would begin almost immediately on the other side, clean defined, a single crisp boundary you could point to on a diagram. Voyager 2 crossed that boundary and found something that looked nothing like a wall. Instead, its instruments detected a broad transition zone stretching more than 100 million miles wide, sitting just outside the heliopause in territory that was supposed to be pure, undiluted interstellar space. Inside that zone, interstellar particles had already pushed inward, tangled with the outgoing solar wind, blending the two environments together across a distance 10 times wider than any model had allowed for. The edge of our solar system, it turned out, is not a wall at all. It is a bruise, a wide, blurred, overlapping region where two entirely different physical environments interpenetrate each other in ways no equation built before the crossing had predicted. If you're the kind of person who wants real space, science explained clearly instead of buried under jargon or drowned in exaggeration, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. The second twist involves a number that, according to every existing model, should never have matched the way it did. When researchers compared exactly where Voyager 1 and Voyager 2 crossed the heliopause, they found something deeply strange. Both spacecraft crossed at almost precisely the same distance from the Sun, roughly 120 astronomical units, despite crossing 6 years apart from completely different directions during completely opposite phases of the Sun's 11-year activity cycle. Voyager 1 crossed near solar maximum, a period when the Sun's output is at its strongest, and its outward pressure should have inflated the heliosphere outward to its largest possible size. Voyager 2 crossed near solar minimum when the Sun's activity is weak, and the bubble should have visibly contracted. Every model built before these two crossings predicted the size of the heliosphere should shift meaningfully between those two states. It did not move in any way scientists can currently explain. Stamatios Krimigis, one of the principal investigators on the mission, a scientist who has studied this data for decades, addressed it directly and without hedging. "We don't understand why that is," he said. Not a cautious guess dressed up in scientific language, a flat, directed mission from a senior researcher that something fundamental about the relationship between the Sun's activity and the size of the bubble that surrounds our entire solar system does not behave the way the textbooks describe it. The third twist is the one that fundamentally changes what the Heliopause actually is, and it is the finding Ed Stone, the Voyager project scientist at Caltech, who has led this mission since before either spacecraft launched, called the most remarkable of all. For years, the working assumption was that the Heliopause functions like a sealed door. Inside the bubble, the solar wind entirely separate. Outside the bubble, interstellar space entirely separate. Two environments that do not mix, do not exchange material, and stay cleanly on their own sides of the line. Voyager 2's instruments proved that assumption wrong in the most direct way possible. As the spacecraft approached the boundary from the southern side of the solar system, its plasma detector picked up a slow trickle of low-energy solar particles already leaking outward into interstellar space before the crossing had even technically happened. Voyager 1, approaching from the northern side 6 years earlier, had detected the mirror image of that exact phenomenon. Tendrils of interstellar particles pushing inward through the boundary from the opposite direction, penetrating into territory that was supposed to belong entirely to the Sun. Two spacecraft approaching from two different directions at two different points in the solar cycle both found the same underlying truth. The Heliopause is not a wall, it is not a sealed door. It is closer to a coastline, with material washing back and forth across it constantly in both directions, in a relationship between our solar system and the wider galaxy that is nowhere near as isolated as scientists assumed. Stone summarized the entire discovery in a single sentence during the announcement accompanying those 5 Nature astronomy papers. The Voyager probes are showing us how our Sun interacts with the material that fills most of the space between the stars in the Milky Way, not how the Sun ends. Now here's why none of this should stay an abstract fact confined to a physics journal nobody outside academia ever reads. The Heliopause is not simply a boundary line drawn on a scientific diagram somewhere in a textbook. It functions as a shield. It deflects the most dangerous high-energy particles produced by exploding stars elsewhere in the galaxy, keeping that radiation from ever reaching the inner solar system, including Earth, at full destructive strength. If that shield is leakier, less stable, and less predictable than every model built from Earth assumed, if it genuinely allows material to pass in both directions in ways scientists still cannot fully explain, then the protective bubble surrounding every living thing on this planet is far more dynamic and far less understood than anyone believed even a decade ago. That is not a minor footnote buried in an academic paper. That is the kind of finding that should sit at the center of how we understand our own planet's long-term safety over geological timescales. Now let's talk about what is happening to Voyager 2 right now, in the summer of 2026, because the story is far from finished and the stakes have never been higher. Every deep space probe of this era runs on power generated by radioisotope thermoelectric generators, essentially containers of plutonium-238 slowly decaying and converting the resulting heat into usable electricity. At launch, Voyager 2 had roughly 470 watts of power available across its systems. Today, nearly 50 years later, it has a small fraction of that remaining, losing approximately 4 watts every single year, with no way to reverse or slow that decline. Engineers at NASA's Jet Propulsion Laboratory have already been forced over the past several years to permanently shut down multiple original scientific instruments simply to conserve enough power to keep the spacecraft alive and transmitting at all. This year, the team attempted something that has never been tried before at this distance, at this age, on hardware this old, a procedure the engineering team nicknamed, only half-jokingly, the Big Bang. It involves a complete simultaneous restructuring of how power flows through every remaining active system on the spacecraft, executed all at once, rather than gradually and incrementally, specifically to minimize the amount of time the spacecraft spends in dangerous intermediate states where automated fault protection systems built into the spacecraft decades ago might detect an irregular power draw and begin shutting components down on their own, with no way for engineers to intervene in time. There is no manual override available. There is no way to pause the procedure halfway through and reassess. Every single command sent to Voyager 2 during this test takes more than 16 hours to arrive, traveling at the speed of light across roughly 13 billion miles of empty space, and every response the spacecraft sends back takes another 16 hours to return to Earth. A single miscalculated instruction transmitted once across that distance could permanently end the mission with absolutely no chance of correction or recovery, and the team at JPL is attempting it anyway, because if it works, the reconfiguration could buy Voyager 2 additional years of operational life. additional years of measurements from a region of space that no other instrument currently built by human hands is capable of reaching. Here's the part of this entire story that deserves to sit at its very center. There is no replacement mission waiting in the wings. There is no backup spacecraft currently sitting in interstellar space ready to take over if either Voyager probe goes silent. If Voyager 2 goes dark, whether from the slow inevitable decay of its power supply or from a failed experimental procedure attempted across 13 billion miles of vacuum, the only other functioning instrument left recording real-time conditions beyond the edge of our solar system is Voyager 1, itself decades old and running on even less power. The next spacecraft theoretically capable of reaching the Heliopause and crossing into interstellar space, if it were fully funded and built and launched starting today. So step back for a moment and actually sit with what all of this genuinely means. A machine built with less onboard computing power than a modern kitchen appliance running on a heat source smaller than what powers a household hairdryer, sitting 13 billion miles from the nearest human being, just forced some of the most respected physicists currently working in this field to admit publicly and on the record that they do not fully understand how the edge of their own solar system actually behaves. The signal from Voyager 2 is still coming, faint, stretched thin by unimaginable distance, delayed by more than 16 hours in each direction, but still arriving day after day, year after year from a region of the universe that no other instrument built by human beings has ever directly sampled. And as long as that signal keeps arriving, there are questions about our solar system, about the shield that protects every living thing on this planet, and about our place in the wider galaxy that only this one specific aging-dying machine is currently capable of answering. If this kind of story is what you come here for, subscribe right now and turn on notifications, because we will be covering the results of the Big Bang procedure the very moment NASA confirms them, and you do not want to miss what comes next. Drop a comment telling me what surprised you most about this story, because it genuinely helps me figure out what to cover next, and share this video with someone who still thinks Voyager 2 is just a footnote to its more famous twin, because a discovery this significant deserves far more attention than the silence it has quietly been given. Thanks for watching.